This video where we are going to look at graphing exponential functions. So our goal is exactly that. Our learning intention is to be able to graph something of the form f of x is equal to a to the power of x. Now this is very different to when we've had x squared and 1 on x, everything, all of the functions we've looked at so far have pretty much just all had numbers in x in it. We've now got this extra a here because this a can also be any number, so we might be dealing with 2 to the x, like we've got here. We might be dealing with 3 to the x. We might be dealing with 5 to the x. It's the a is the placeholder for a number, which can be any number, but the key thing is that an exponential, we have the index or the exponent is our variable, technically. So we're just going to look at a couple basic examples. We're going to substitute some values in and then plot those values and have a look what we get so we have an idea of why the exponential graph looks the way it is. So we're going to start with the really easy stuff. We'll start over here on the right hand side. So if x is 1, y is going to be equal to 2. If it's 2, that's going to be 4. 2 to the power of 3 is 8. And 2 to the power of 4 is 8 times 2 is 16. So as you can see, they grow, and they grow pretty quickly. We go up plus 2, we go up plus 4, we go up plus 8. That's that whole idea of exponential growth, is that it's growing every time. Same down here, we get 3, we get 9, we get 27. 27 times 3, 60, 81, I think it is. So we get that. But now let's also have a look at this, I guess the center we'll call when x is 0, and then the left-hand side. So when x is 0, our power is 0. This is where we need to use the zero power law. Whenever the power becomes 0, well, then the whole thing just becomes 1. So both of those are 1. Now, what about these negatives? So we've got 2 to the negative 1. Well, we know from the negative power law that we can rewrite that as 2 to the power of 1, which now becomes 1 over 2. And we can keep applying that. We now get 2 to the negative 2, so we can write that as 1 on 2 to the 2, so that becomes 1 on 4. And we can do the same over here. We get 2 to the negative 3, so that's the same as 1 on negative 3, which is equal to 1 on 8. And we could recognize that that pattern goes again. We can see there's a 2, ends up 2 on the bottom. We have a 4, we end up with 4 on the bottom. And that pattern keeps going over and over and over. So this is going to be 1/3, this is going to be 1/9, this is going to be 1 on 27. So what can we notice about the patterns from this? Well, from at 0, it's always at x equals 0, y is going to be equal to 1 in this most basic form. As we go larger than 0, we get really big really quickly. And then when we're less than 0 over here, we're getting smaller and smaller. We get half, a quarter, 1/8, or if we're doing to the base 3, we're getting really small really quickly. The thing to note is, have we gotten to 0 and did we actually get any negative values? Well, if we try to get 0 as equal to 2 to the x, like say if we're saying let y equals 0 because we're trying to maybe find the x-axis intercept, there is no solution to this. Doesn't matter what power you choose to put in there, you can't get 0, because even if we let x equal 0, well, 2 to the 0, we know 2 to the 0 is equal to 1. So we can't get 0 that way. So it doesn't matter what number you put in there, negative, positive, decimal, whole, we can never actually get y to be equal to 0. So from this, there is a key thing that we get. We have a asymptote at y equals 0. So let's draw that in for our basic shape. And that's one conclusion we can draw. For this basic shape, we can see that it's when x is equal to 0, but we'll just say when the power is equal to 0, y is going to be equal to 1. Okay, so whatever, we can make this more complex up the top there, but when that whole top bit becomes 0, well, the y value is going to be 1, so we're always going to go through 1. What other conclusion we can draw? Well, as x gets bigger, y gets really big. So we get that sort of shape going on. So let's actually put it in. That's 0, 1. At 1 we got 2. So I'm just doing y equals 2x here. At 3 we got 8. So 3, 4, 5, 6, 7, 8 up there. And then 9's going to be way up there. So we get... Oh, the end of that line's not great. But you get the idea. Okay. We get this shape. We have an asymptote at y equals 0. It grows really quickly, and then it keeps getting smaller and smaller and smaller going this way, but never approaches 0. As we change this a number, as we make it bigger, as we saw when a was 3, we get bigger even quicker. So if I put that one in, let's put that in red. It still goes through 0, 1, but it's going to go through there, and it's going to go through... I forgot to put the 4 in. My bad, on this previous one. I missed a number. When x is 2, y is 4, it goes through there, then through there. That is y equals 2 to the power of x. But if we do y to the 3 power of x, 3 goes up to 9. 9's there. We get something that looks like that. So that's our shape. It's exponential. It grows really, really quickly. Right, how are we going for time? That took a little bit too long. So here's a couple quick looks at the trends that we can pull out of. At x equals 0, it's going to go through 1. When x is equal to 1, it's going to go through whatever the base is. So if it's y is equal to 2 to the power of x, when x is 1, it goes through 2. If y is equal to 15 to the power of x, when x is 1, it's going to go through y is 15. And then we get the reciprocal over on the left side. So if we had y is equal to the power of x at -1, it's going to go through 1 on 2. If y is equal to 3, let's pick a different number, 5 to the x, at x is equal to -1, y is going to be equal to 1 on 5. So it always has that sort of decrease or flipping. The other thing we need to note is if we make x negative, if we make x variables negative, it's like doing a reflection. It just flips it about the y-axis. So that's what we have there. When the base is a decimal, it would be the same using the index laws of actually you could rearrange it to make it so that it's a negative power. So if the base is a decimal between 0 and 1, it's actually going to look like this over here of a negative power. Right, let's break it down. We started with a very simple form there, but let's think about, because like always, we've transformed everything. So what is the general form? Well, we started with y equals a to the x, and let's add our translations first. And our translations, h is always with x, k is always stuck on the end, so we're going to get y is equal to the ax minus h, and then plus k on the end, not in the index. Now we just need to add on our dilations. So if we dilate from the x-axis, it would be like replacing y on b. If you remember transformations, replacements, dilate from the x-axis, it's affecting the y-coordinate, so you replace y on b, which is the dilation factor. We get ax minus h plus k, which is the same as y is equal to b ax minus h plus k. All in brackets. And then we could show the same for dilation from the y-axis, but it's replacing x with x on the dilation factor. And I've just put, technically this is in brackets. If you want to read the h value properly, whatever the x is divided by, you need to get this h inside brackets to read the translation properly. But that's the general form. H translation, K translation, B dilation, C dilation, and as we've shown, we can also change the base, and that sort of acts like a dilation from the x-axis, because that in itself, if we changed A from 2 to 3, that's also going to make the graph grow quicker. Rightio, sketching. Just like everything else, we've got a set of steps that we really want to follow. First off, we want to identify the shape. Is it going up like that? Is it reflected that way? Is it flipped down? We just need to check which ways it's reflected and what the sort of translations are. Then we want to find the horizontal asymptote, and then we need to draw it on the sketch and label it. Find any x and y intercepts if they are present. Find a reference point if required, and then sketch the curve. I cannot stress enough how important this step 2 is. Of course, step 1 is super important, but step 2 is really important because that's going to save you a lot of issues with step 3. A lot of people, when the graph is translated up, well, we've got an asymptote there, it goes like that, and then people try and find an x-intercept. Well, it's quite clearly from this asymptote, there's no x-intercept. There's going to be nothing crossing the x-axis. So identify your k value really quickly and identify any reflections. That's going to make your life a lot easier. So let's go through these steps, how I would do it. Okay, sketch the graph of 2 to the power of x minus 1 plus 2. So the very first thing I'm going to look at is 1, do I need to factorize in here to get this just as a regular x? Is there negatives in front of it? Is there any divisions? Because if there's anything like multiplied out here, I need to get it in brackets to read my h value properly. After that, I'm going to start listing all my values. So h, clearly in this case, is 1. We switch the sign of it. K is equal to 2 because we don't switch the sign of k. And there is no reflections because there's no negative sign in front of the x and there's no negative sign out the front. They would be our 2 reflections. So we've got no reflections. So straight away, h is 1, k is 2. So k is going to be where my asymptote is. Okay. So we've translated up because normally it's here at y equals 0. But we've translated up 2. So there's my asymptote there at y equals 2. Okay. Now we know normally that when x equals 0, it goes through, or 1 or whatever it goes through 1. But we can also see from this that is translated 1 to the right. So this point is also going to be moved across 1 to the right. Reading or recognizing, okay, when x is equal to 0, and then looking at what the h translation is going across 1, can run you into some issues sometimes, especially if there's a lot going on up here. So what instead I suggest is, as it says here, is we found the horizontal asymptote, and then straight away think of the shape, and we know it's going to go like this, so we know we must have an intercept here somewhere. So step 3 was, that was step 2, step 3 was find the intercept. So we're going to let x equal 0. Here we're finding the intercept. So if we let x equal 0, we get y is equal to 2 to the 0 minus 1 plus 2. So we get y is equal to 2 to the negative 1 plus 2. Now 2 to the negative 1, we know from the index law we can change that as 2 to the power of 1. Get plus 2 is equal to half plus 2, which is equal to 2.5. So we found our intercept right there, which is 0, 2.5. And now we can just draw that in like that. And that is our function. You could find another point later on. You could let x equal 1, x equal 2 to help with your scale. But for now, that's technically enough to do the graph. You've got the asymptote, which is critical. You've got its intercept, and you've got the rough shape. That is fine. So the key with these exponentials is the k value. Really need to find the k value and check for reflections. Other than that, the h, you can use it, but I'd suggest it's always just much better. Check your k and then find any intercepts. Rightio, we have 3 to the negative x. Okay, so the x value itself has been made negative, or x is replaced with negative x if we think in terms of our transformations and inspection. So that means our x coordinates are being flipped about the y-axis. So in this case, we are reflecting about y-axis. So we know now our shape is going to, oh, terrible drawing, instead of looking like that, is going to be flipped and is going to look like that. So that's our basic shape. So that's sort of step 1. Step 2, we need to identify h and k. H is 0, k is 0. So we know my asymptote now is y equals 0. Just drawing in roughly, it's going to look something like that, but I'm going to find an intercept, and we know we have a y-intercept, so I'm going to let x equal 0. Let me put a little title here. Finding the y-intercept. So we let x equal 0, so we get y is equal to 3 to the negative 0, which is 3 to the 0, which is equal to 1. So now we can go back in, put in our proper dot. We're at 0, 1. And we get something like that. There we go. That's it. Labeled asymptote, labeled key point. Done. Okay. Now, because the negative's out the front, it's not directly applied to x. If we have the negative out the front, if we applied it directly to something, we could rewrite this as negative y is equal to 3 to the x. So we can see that y has been replaced with negative y, so that means our y values are being switched about, so we're reflecting about the x-axis. Okay, so we know then, instead of it looking like that, we're actually now going to have something flipped upside down. We flipped about the x-axis. From there, we want to recognize our h and k, which is both, what did I write to? I was thinking step 2. That's step 2. So we know our asymptote, which we must label as at y equals 0. We must draw it in, we must label it. And straight away we can recognize there's nothing else going on up here. So remembering that pattern, if up the top is equal to 0, which it will for our y-intercept, the whole thing becomes 1. But just to prove, find our y-intercept. So we let x equal 0. We're going to get y is equal to negative 3 to the 0, anything to the power of 0. And technically that power is being applied unless there's brackets drawn. If you see this negative 3 to the x, it's technically that. So we get negative 3 to the power of 0, so we get negative 1 times by 1, which is negative 1. So we go through there, that is 0, neg 1. We are going to get something like that. There we go, all done. Put this asymptote label there, just to avoid confusion. Now we start looking at some dilations. This is where it just gets a little trickier, especially if you add in some translations beforehand. But same thing, you want to have a look at what is the shape. Is there any reflections? Is there any negative signs? Well, there's no negative with the x, there's no negative out front, so it's just going to be a standard shape like that. Step 2, we want to identify our h and our k values. In both these cases, there's no h up here, there's no k at the end, so we have a h of 0 and a k of 0. Yeah. Okay, so our asymptote is not affected. So our asymptote is at y equals 0. We can put that in. Step 3, we know we're going to have an intercept, so let's find the intercept. So we're going to let x equals 0. So we get y is equal to 0.2 by 8 to the 0, which is equal to 0.2 by 1, which is equal to 0.2, or as it says up here, 0.2 is the same as 1 on 5. So our intercept is actually there, which is 0.1/5. So we get something like that, and the whole graph is flattened out. And you could check that too by substituting in a couple values if you wanted to check. So we could also do let x is equal to 2, so we get y is equal to 0.2 by 8 to the 2. The base of 8 is actually quite large, so this will still kick up a bit. 8 squared is 64, so 0.2 by 64. 1/5 of 64, is that 12? It's 12 point something. Yeah, it's 12.1 or something thereabouts. I'm just estimating. I don't have my calculator on me. So it's actually really flat and then still kicks up massively because of that 8. Goes and then whoo, it'll kick up like that. Go up really, really quickly. So that is why some x equals 2, but that's still why it is always handy to maybe do a check, a couple x values across, just to get a sense of the problem. Lastly, finally, we have dilations from the y-axis. So you can see here we've got x on 2. So if we think of the standard form a to the x, and because it had the base of 9, we've now got 9 to the x on 2. So I've replaced x with x on 2, so that's my dilation factor that you can read off. But again, for these, it's the much easier way is look at the shape, check for any negatives. So step 1, check for shape check, which is mean check for negatives. There's no negative with the x, there's no negative out the front, so we just know it's going to look like that. Step 2, identify your h and k values. H is 0, k is 0, so straight away we still know our asymptote is y equals 0. Step 3, we know there needs to be an intercept, so let's find that. So find our y-intercept, we let x equal 0, we get y is equal to 9 on 0 on 2, which is equal to 9 pair of 0, which is equal to 1. So we're going through 0, 1. And like I said in the last video, maybe we want to find another point just to get a bit of a sense of scale. So I'm just going to let x equal 1. So I get y is equal to 9 to the half. Now we know that's the same as square root, which is equal to 3. So we're going to be going through there. So it still kicks up a bit. There we go. Now that's 23 minutes, so I apologize for a little bit of a long video, but I wanted to go into this with a lot of examples. What are the takeaways? What are the summaries? Let's go back up to this. This process will help you a lot more than trying to remember that. Okay. Identify the shape means check for negative. Check for neg x or neg out the front. And just remember which one does which reflection. Because again, the whole point of that is just doing a little sketch at the side. Is it going to look like that? 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 Once you have that, then the rest is really easy. Because then you just check your h and k. That's what this is. Find h and k. More importantly, it's just k. And then find an intercept as necessary, and then add points of reference as needed to help get a sense of scale. That will lead to a much more accurate graph than trying to remember all of this and thinking, okay, my h value is 2, so that's moved up. Then I've got this b value, so that's dilating from the axis, so that's all stretched like this. that will lead to confusion and issues with mental pictures. It's much easier to do this because you're just going to draw in a dashed line and then play connect the dot. And that'll lead to a much more accurate graph. If you have any questions, please ask as normal. Thanks and have a good afternoon.